All right, subscribers, welcome back to another episode of Science with Surbeck. Today we're starting off with section 13.1, which begins our units on each of the states of matter. And so in section 13.1, it deals specifically with gases. Now, before we get into the details of the notes, there are three objectives I want you to be able to accomplish by the end of this video. Objective number one, use the kinetic molecular theory to explain the behavior of gases. Objective number two, describe how mass affects the rates of diffusion and effusion. And objective number three, explain how gas pressure is measured and calculate the partial pressure of a gas. So we begin our in-depth look into each of the three states of matter. And to describe matter, what we're going to use is the kinetic molecular theory. Now, oftentimes we're going to abbreviate the kinetic molecular theory as KMT, kinetic molecular theory, as our abbreviation. Now, kinetic molecular theory is simply defined as a model that describes the behavior of matter in terms of particle in motion. So the kinetic molecular theory is going to explain the different properties of solids, liquids, and gases. Now, something else to be aware of is that not only does the kinetic molecular theory help explain the differences between solids, liquids, and gases, but we also have to take into account in terms of the atomic composition affecting these chemical and physical properties of each state of matter. Now, the kinetic molecular theory makes several assumptions. One of the main assumptions that are made by the kinetic molecular theory is the size of particles. The other assumption is the motion of the particles. And the third assumption is the energy of particles. Now, keep in mind, too, that the kinetic molecular theory was designed or centered around explaining what happens in terms of the gas particles that we encounter. So as we describe these assumptions, we're doing so as if we are making these assumptions for a gas. So that's important to keep in mind. So let's go through each of these assumptions, and we'll start with the particle size assumptions. So the kinetic molecular theory states that gases consist of small particles separated by empty space. Okay, so if we imagine this, what I just stated, we could have something like this. Let's say we have a gas, and it's in a closed container of sorts, and this gas is going to be a really small particles here, and that's what I'm representing with these dots. And in between these gas particles is just empty space. And we'll draw some arrows to that empty space. And so as you can see, there is quite a bit of empty space in between each of these gas particles. And that brings us to our next point here, is that gases are too far apart to experience any significant attractive and repulsive forces. And this statement comes back to the fact that gases, which are these little small particles, have so much empty space between each and every gas particle that they can't have that pushing or pulling experienced by the positive protons or the negative electrons. So thus, they have very little attractive force, so much so that we say, hey, it's not really a big deal about what significant force they do experience. Now, let's turn our attention to this particle motion assumption. So the particle motion assumption of the kinetic molecular theory says that gas particles are in constant random motion. And so if we go back to our picture here, we have our glass container, and it contains some gas particles here. We can put these gas particles, and then with a different colored pen, I can show you that these gas particles are always moving in this constant random motion here. And this is a pretty big deal here that we make this assumption. And one of the big deal, or one of the main points here, is that we have this. Particles are going to move in a straight line until they collide with either other particles or the walls of a container. Okay, so if we explain these 2 points here, this makes a perfect depiction of what we have in our picture. So as these particles move around, they're moving in this straight motion until they hit that side of the container, or they happen to bump into one another. So what that means is that empty space in between each and every gas particles is not going to affect that motion of that particle. Now, with the collisions, we need to talk about what type of collisions they are. And they are elastic collisions. And what an elastic collision means is that it's a collision that there is no kinetic energy lost. So since no kinetic energy is lost when these particles, these gas particles collide, what happens is this. The kinetic energy is transferred between particles, but that kinetic energy inside that component or inside a particular mixture of gas is not going to change. Okay, so that is our second of 3 assumptions we make with the kinetic molecular theory. The next assumption is the particle energy assumption. So with the particle energy assumption, we have this. The kinetic energy of a particle is going to depend on the following 2 factors. The first factor is the mass. The second factor is the velocity of that particle. And so the kinetic energy of a particle can be calculated using the following formula. And this formula, you may have seen it before in some physical science applications or some physics application, and that is this. The kinetic energy is equal to half times the mass of the gas particle times the velocity squared. Okay, so remember, our KE is standing for kinetic energy, our M is the mass of the gas particle, and our V is the velocity of our gas particle. Now, just as a reminder, the V for velocity has 2 parts. One, the speed, where we see it usually in meters per second, but also we see the direction. So it's dependent upon 2 factors, and that's something to keep in mind. So let's go through some examples here. So with this in mind about kinetic energy, we have this. Gas particles. If we're dealing with a sample of gas, they are going to be assumed to have the same mass, but not all are going to have the same velocity. Now, if you take this statement here that we just made, and we assume in a gas sample that each sample has the same mass, but those particles are moving at different velocities, what this statement results in is that each particle is going to have a little bit different kinetic energy. Now, our final thing that we can do here with our particle energy is associate kinetic energy to temperature. So we have to keep in mind that temperature is a measure of the average kinetic energy of the particles in a sample of matter. So what we can assume is that at one temperature, again, keyword, at one temperature, all gases are going to have the same kinetic energy. Okay, so those are 3 assumptions of the kinetic molecular theory. And just as a reminder, these were designed around describing the behavior of gases. Now, we later found the implications and the significance of being able to apply this information to our solid and our liquid states of matter, but we get to that later down the road. So let's transition now to specifically talking about gases, and I want you to keep in mind these 3 assumptions that we've just made about the kinetic molecular theory. Okay, so with our gases here, number 1, the kinetic molecular theory is our main way in which we explain the behavior of gases. So I want to start off here with our basic properties through 2 examples. The first example is a gas filling up a flotation device. So let's say we have this inflatable life raft and we take into consideration what we know about gases. Well, gases are going to have this constant motion that's going to allow that gas to fill, to expand to that container. This helps explain why a life raft stays inflated when air is blown into it. And then another example here is a life jacket. What a life jacket does is it allows a person to float in water because the air molecules inside that life jacket, which are a gas, are less dense than the liquids or solids that person is floating on top of. Okay, so now we have some ideas of a gas and what they can do. Now we're going to get into some details of the properties of gas. So the first property of gas here that we're going to talk about in depth is the low density of a gas. And the reason that there is a low density of in a gas is because there's great amounts of empty space between gas particles. So if you can remember our picture from earlier, if I draw my gas container again, remember our gas particles are these really tiny particles, and then in between those gas particles is just empty space. So this empty space is a pretty significant deal when we talk about the properties of gases. This empty space results in that low density of gases. Now, again, the empty space is going to result in a very low density of gases. So let's take this idea here, or our concept of a low density, and let's go through some examples. And so that example is going to be the density of chlorine. Gaseous chlorine has a density of 0.00293 grams per milliliter. And solid chlorine has a density of 3,200 grams per milliliter. Again, this is a comma, so it's 3,200 grams per milliliter. That is a very significant difference between the gaseous and solid chlorine. So you can see how low of density a gaseous state of matter is. Now what we need to talk about here is how the gas can be compressed or expanded. So with our compression and expansion, we have to remember this. There is a large amount of empty space between gas particles, and so it is going to allow gas particles to easily be pushed or compressed into a smaller volume. Something to keep in mind is that when a gas is compressed, the empty space between gas particles gets reduced. And then what we also have to remember is that gases can fill the available space of its container because it is in that constant random motion that we see in a gas. Now, putting this expansion and compression business into an example here, one really good example is squeezing a balloon. So when you take a balloon here and you squeeze it, what happens here is that we reduce the empty space in between the gas particles, and we compress this air that's in the balloon into a smaller volume. And so what this does as we squeeze the balloon here is that it greatly increases the pressure that is experienced on the container, which is the balloon. Now, when we take this same balloon that we did squeeze and we let go, what happens here, you can see the balloon gets deflated, and that's because the gas particles are occupying more volume. And just the opposite is occurring here, is that when we let go of that balloon, the pressure of the balloon is going to decrease. And again, all of this can happen because of the basic properties of a gas. The gas particles are really far apart. They have empty space, so that allows us to squeeze them closer together as we compress a certain volume. And then as we release that pressure, the gas is allowed to expand more volume, and thus you reduce that pressure. So now we're going to shift gears here and talk about another unique property of a gas, and that is diffusion. Okay, so diffusion is just going to be defined as the movement of one material through another. Now, we should know that for a gas, this diffusion is going to happen because gas particles diffuse from an area of high concentration to an area of low concentration of gases. So we have to think why this happens. Why do gases diffuse from areas of high concentration of gas to an area of low concentration of gas? And we have to remember two pretty important things. Number one is that gas particles can easily flow past one another because the kinetic molecular theory assumes that there is no significant forces of attraction between gas particles. And the other reason that diffusion occurs in gases is because gas particles move in random direction until they mix evenly throughout a distribution. So now that we have this information in mind, we can talk about the rates of diffusion with gases. And for the most part, the rates of diffusion are going to depend on the mass of the gas particle. The lighter the particle is, the more rapidly a particle or a gas will diffuse. So now I want to go back to a statement that I said earlier, and that was this. With our kinetic energy, I said at one temperature, and again at one temperature, we are going to assume that all gases have the same kinetic energy. And if they have the same kinetic energy, that means that depending on if we have a light or heavy gas particle, will determine a few things. So at one temperature, the kinetic energy is the same for all gases. This means that particles that are heavier are going to have a slower velocity than particles that are lighter. What this means here with lighter particles, and I know I'm going to squeeze it in here, they are going to diffuse more rapidly or diffuse faster. So the lighter the gas is, the faster it moves, the faster it diffuses. And now what this brings us to is a concept of Graham's law, talking about the rate of diffusion and effusion. So Graham's law is talking about effusion, and effusion is where a gas escapes through a tiny opening. And so an example of this is if we took this balloon that I've been playing with here, and I poked just a real small, not even a pencil size, but a real small pinhole, and we watch the gas slowly escape out of that one tiny opening. So that brings us to Graham's law. And so what Thomas Graham did is he performed an experiment to measure the rates of effusion. And what he did in his experiment is he looked at how gases effused into a vacuum. And his results of the experiment led to his law, or Graham's law of effusion. Now, this law states that the rate of diffusion for a gas is inversely proportionally to the square root of its molar mass. Now, easier for us is a formula. And so this formula for Graham's law is as follows. The rate of effusion is equal or is proportional to 1 over the square root of the molar mass of a gas, or of the gas that you're looking at. Okay? And so these are things that are pretty simple that are put into terms that we can actually go through a calculation. So let's do this. Let's use this concept of Graham's law, and let's go through a problem here. So our problem here, it says ammonia, which has a molar mass of 17.0 grams per mole, and hydrogen chloride has a molar mass of 36.5 grams per mole. We want to know the ratio of their diffusion. So we should know this, that if we use Graham's law, we can set up a proportion to compare the diffusion rates for two gases. So how they do this is they utilize Graham's law of effusion to develop this formula. And that is this. We take the rate of gas A, divide that by the rate of gas B, and we set this equal to the square root of the molar mass of gas A divided by, the molar mass of gas B divided by the molar mass of gas A. So you notice here, rate A is on top, but when we put it in the square root business, the molar mass of that gas here is on bottom. That's important as we go through here. So for these things here, it's very important that we identify and distinguish our gas A and gas B. So for gas A is going to be the first gas listed in our problem. Now, gas B is going to be the second gas listed in our problem. So in our problem here, we have this. We have our first gas, which is ammonia, and we are going to call ammonia gas A. So I'm going to put this out to the side. Gas A equals ammonia, which has a molar mass of 17.0 grams per mole. Now, our second gas is going to be our gas of hydrogen chloride, and I'm going to abbreviate that HCl, and that has a molar mass of 36.5 grams per mole. Okay, so now we are trying, our goal is to find this ratio, this rate between rate A and rate B. So what we are going to do is this. We're going to take this square root, and on top, we are going to put the molar mass of gas B, which in this case is hydrogen chloride. That is 36.5 grams per mole. Okay? Then on bottom, we put the molar mass of gas A, which in this case is ammonia, and that is 17.0 grams per mole. Then all we have to do is calculate, but just be careful because we do have this business of the square root. So I'm going to get the square root on my calculator, and I'm going to put 36.5 divided by 17.0. Make sure you close that parenthesis for the square root, and I get a value of 1.47. Now, this right here, this value of 1.47 is unitless because it is just comparing rate A to rate B in a ratio. So whenever it asks, hey, compare those diffusion rates between these two gases, well, that is what you would calculate. Now, the important thing for us is that the first gas that is listed is gas A. So gas A equals first gas that is listed. That is very important as you go and you do some practice problems. So now that we have talked about a little bit of Graham's law and the effects of diffusion and effusion, we can move on to another topic here in the subject of gases, and that is with our pressure. So pressure is defined as the force per unit area. And we have to remember that gas particles exert pressure when they collide with the walls of their container. Now, what we have to remember with this is that an individual gas particle is going to have very, very little mass. Thus, it's going to exert little pressure. But what we have to remember is that in something like 1 liter, there is approximately 1 times 10 to the 22nd gas particles. So with that many gas particles, and that is a lot of gas particles, with that many gas particles, the particles that are colliding can cause a pressure that is substantial and measurable to us. And so now we can change our gears or shift gears to what we know as air pressure. So air pressure is defined as the pressure created by air particles that are moving in random direction within Earth's atmosphere. So at Earth's surface, the air pressure is approximately equal to the pressure exerted by a 1 kilogram mass on a square centimeter. So again, the air pressure at the surface of Earth is approximately equal to a 1 kilogram mass on 1 square centimeter. Now we have to remember that air pressures are going to vary depending on the location in which you are at in the world. For example, the air pressure on top of a mountain is less because there is less air pushing down on you. Now at sea level, the pressure is normally going to be the greatest because that is the location where there is the greatest amount of air pressure exerted on one location. Now, to measure air pressure, what scientists have developed are barometers. And the first barometer was invented by a scientist with the name of Torricelli back in the 1600s. Okay, so with all this business on pressure, we need to focus in on the units of pressure that are used throughout our calculations. So with our units of pressure, we need to understand that the SI unit for pressure is the Pascal. And 1 Pascal is equal to 1 Newton per square meter. And if we want to abbreviate that, that would be 1 PA is equal to 1 big capital N per meter square. Okay, so now we have this chart down here that's on your notes, And you can see that there are many more common units used for pressure that we have. For example, the engineers typically use PSI. And PSI stands for pounds per square inch. Now, barometers that are typically used usually report their readings or their measurements in millimeters per mercury. Now, you can see from the chart here that there are other typical units that we utilize for our units of pressure. Now, a couple of units I want you to become familiar with and their equivalent are as follows. The first is that 1 atmosphere, 1 ATM, is equal to 760 millimeters per mercury. The other conversion I want you to become familiar with is that 1 atmosphere, ATM, is equal to 760 torr, and 1 atmosphere is equal to 101.3 kilopascals. So these are things that we'll see again when we get to our unit that's totally dedicated to our unit on gases. We will revisit these and review these, but I want you to become familiar with these now. All right, so now what we have to do, our last bit of business here, is to talk about Dalton's law of partial pressure. So Dalton's law of partial pressure states that the total pressure of a mixture of gases is equal to the sum of the pressure of all gases in the mixture. And more easily to see this statement here is in our formula. And so our formula for Dalton's law of partial pressure is this. The total pressure, which I'm going to label it as P total, is equal to the sum of all of the gases here. So I am going to come out here and I'm going to say P to the N, okay? So the total pressure is the total pressure of all of the gases in the mixture. And this business on the right here, where it goes P1 plus P2 plus P3 plus Pn, which is the last gas, is the partial pressures of each gas in the mixture. Now, what we need to remember here is that when John Dalton conducted his experiments, he found that each gas in a mixture exerts pressure independently of other gases present in the mixture. So with that knowledge, we can determine that the partial pressure in a gas of a mixture is going to depend on the number of moles of gas, the size of the container, and the temperature of the gas. It does not depend on the identity of the gas in the mixture. So let's go ahead and try out Dalton's law of partial pressures in an example. Okay, so we have here a mixture of oxygen, carbon dioxide, and nitrogen, which add up and have a total pressure of 0.97 atmospheres. We want to know what is the partial pressure of oxygen if the partial pressure of carbon dioxide is 0.70 atmospheres and the partial pressure of nitrogen is 0.12 atmospheres. So the first thing that we must do is establish our formula. So in this case here, the total pressure, so the total pressure, P total, is equal to the pressure of oxygen plus the pressure of carbon dioxide plus the pressure of nitrogen. And so from here, all we're going to do is plug in what we know and what we don't know. So the total pressure in this particular instance is this. It said the total pressure inside the container is 0.97 atmospheres. And we need to find out what is the pressure of oxygen. So the pressure of oxygen would be our question mark. And the pressure of carbon dioxide is given at 0.70 atmospheres. And then the pressure of nitrogen is given at 0.12 atmospheres. So we found out what we know, and we can now solve for what we don't know, which is oxygen. So all I'm going to do is plug these numbers back into my equation. And the reason I can do this is that they all have the same unit. So that's something to check for. So we're going to have 0.97 atmospheres equal to the pressure of oxygen plus the pressure of carbon dioxide, which is 0.70, plus the pressure of nitrogen, which is 0.12. Now, to get oxygen by itself, we are going to subtract 0.70 from each side, and we are going to subtract 0.12 from each side. So in my calculator, what I'm going to do is I'm going to type in 0.97 minus 0.70 minus 0.12, and I'll press enter. So the partial pressure for oxygen is 0.15 atmospheres. And that is how we would utilize Dalton's law of partial pressure. All right, so you may be wondering, okay, well, what is the point of Dalton's law? Well, it helps serve a couple of things. So, number one, it can be used to determine the amount of gas produced by a chemical reaction. So let's say you have an equation such as hydrochloric acid and zinc. When these two substances combine together, the products are zinc chloride and hydrogen gas. Okay? Now, we can balance this equation here to be as follows, and everything is balanced there. But what we can do here is this. We can collect the amount of gas that can be produced from this reaction. Now, when we collect this gas via water displacement, we're going to have a combination of air and the gas from the hydrogen. So using Dalton's law of partial pressures, we could do this as follows. So the total pressure inside this container that we've collected would be the pressure of hydrogen plus the pressure contributed by air. So thus we could figure out, well, in an experiment, how much hydrogen is actually collected. Now, what we could also do here is use the partial pressures of gases at the same temperature and relate it to the gas's concentration. So we have to remember here that the pressure of water vapor is fixed at a given temperature. And a calculation can be made to determine the partial pressure of hydrogen. Now, one mistake I did make here is that this, when we collect via water displacements, this shouldn't be air. This right here should be water vapor. And so, again, this is not the pressure of air, but the pressure of water vapor. Again, not a huge mistake here, but we should note the difference. So there are some applications here for Dalton's law of partial pressures. All right, so this concludes this section of notes. I know it's been quite the lengthy section. Hope you've hung in there. Hope you've enjoyed this video. And if you haven't already, make sure you have subscribed.